Okay, hi science bowlers. So this is a video on electromagnetism. So I decided to write out a few things prior. Okay, here's the deal. Changing electric fields or moving charges induce or create a magnetic field. And changing magnetic fields induce electric fields, which can be related to currents or potential differences. So let's see if I can get some good colors going here. Changing electric fields, so let's do like a sine wave. Changing electric fields induce magnetic fields. Let's see if I can do this. This is like supposed to be in the other plane, 90 degrees. This is so much better when I can stand up and show you. Okay, so here, this is in like the horizontal plane, and this is vertical. Okay, so this was the electric field oscillating up and down, and that induced a magnetic field going in and out, sort of the plane. And then, what is that? What did I just draw? Oh my gosh, it's an electromagnetic wave. This, my dear friends, is light. Okay, this vector right here is called, hilariously enough, the pointing vector. That's P-O-Y-N-T-I-N-G. It was a guy's name, right? But it literally points in the direction of the light propagation. And so that is the gloriousness of light. So what actually governs how these guys affect each other? That is the glory of Maxwell's equations. Okay. So what you will see, you do not need to like memorize these at all, but what I want to point out are a couple of important points about these. Okay. Let me just, and this is this is more sciencey than science bully, but let me just sort of show you the glorious symmetry. These are surface area integrals. These are line integrals. Okay. So there's a surface area integral of an electric field and a magnetic field, and then a line integral of electric field and magnetic field. Okay. This is called Gauss's law. And this quantity of that surface integral of the electric field is called flux. And when you think about flux, think about it as sort of the amount of stuff going out of an area. Okay, so this is the surface integral of the electric field over a closed surface. We're really measuring like how much field is coming out of that surface. Okay, and that's related to, right, the charge that's enclosed by the surface. And it is totally reasonable if you have no idea what I'm talking about right now. But Gauss's law talks to you about the electric flux, right? So electric flux is given this, or electric flux would be phi sub E here. Phi sub B is the magnetic flux. And then this, of course, is your permittivity of free space, which we keep seeing every time with the electromagnetism stuff. Okay, this looks so familiar. This is saying the phi sub B, right, the magnetic flux, is equal to 0. This is called Gauss's law for magnetism. And so basically it's saying that there are no magnetic monopoles, nothing that can create that flux like a charge can. Okay, that's all nice and good. Cool. This is called Faraday's law. Oops. Faraday's law of induction. So, integral of E dot dl is also a potential difference up to a sign. This is the magnetic flux. Oh, by the way, this is a partial derivative. It's in Calc 3 or whatever. I don't know, multivariable calculus. But just think about this as a derivative. This is a time derivative of magnetic flux. So it says if magnetic flux is changing, so if you have a changing magnetic flux, that induces a potential difference. And potential differences create currents. So we're going to do a whole thing on induction on the next page. Okay, but that's Faraday's law of induction. This is Ampere's law. Looks a lot like Gauss's law. It's this line integral. You got this mu naught instead of epsilon naught, and you have a current that's enclosed. Cool. And then this is Maxwell's correction to Ampere's law. And it says that a time-changing electric flux also creates a magnetic field. Okay? And then, here it is, ladies and gentlemen. This is where I get so excited. Mu naught and epsilon naught, right? Mu naught kept coming up in the magnetism stuff. Epsilon naught kept coming up in the electric stuff. Now, here, we have something that brings them both together in the same part of an equation. And here it is. Mu naught times epsilon naught is 1 over the speed of light squared. This is one of my favorite things ever, ever, ever. Oh, it's so beautiful. Okay. All right. Let's get a little bit more practical on induction, and then we're done. All right. So, induction. So remember that solenoid? Whee! What they noticed is that, okay, here, sorry, we hook this up to a galvanometer. A galvanometer is just a really, sensitive ammeter. Okay, so this is a magnet. This is a wire with no battery. Okay, this is just a coil of wire hooked up to an ammeter. And what they saw was that if you moved the magnet right into the coil, then you get a current. So hold on, you get a current with no battery. Something cool is going on here. So there is a magnetic flux, right, through these coils. And if you move the magnet in, then you will get more magnetic flux, okay? More magnetic flux. So if the flux changes, you get a potential difference, okay? What's also fun is if you move magnet out, you get a current the other way. Okay, so this is Faraday's law of induction that we saw. It was one of Maxwell's equations. And the idea is that nature hates change. So here's what's happening. We had a certain amount of flux. Okay, so a certain amount of magnetic flux, which is equal to the magnetic field strength times the area. Okay, if I then move the magnet in more, I have increased the flux. Okay, what nature is so annoyed by this that it says, you know what? I am going to create a current, okay, that will create a magnetic field to oppose this. So I don't want this. I want a magnetic field out. So I'm going to create a current this way. Okay, I know, it's so cool. So it's going to induce a current to oppose the change. And remember that current is related to a potential difference, right? And that potential difference and the potential, remember the EMF is like a potential difference. The induced current is equal, times the resistance of that is equal to the induced EMF. And d phi dt. So, sorry, I really messed up my spacing here. But this is Faraday's law. And it tells you, what's really fun is that this negative sign is called Lenz's law, just the negative sign. And that tells you the direction of the current. It tells you that that's the nature hates change part is Lenz's law. Okay, that was maybe not my most elegant video, but there it is. Hope you learned something.